Hey, this is our next INB on rational equations. It's going to be called graphing rational equations. Don't forget, a rational equation is just two polynomials divided by each other. There's a polynomial in the numerator, and then we have a polynomial in the denominator, and they're dividing with each other. Just remember, the polynomial in the denominator, q of x, cannot equal 0. And when it does, we have points of discontinuity. And those are where our vertical asymptotes, and today we'll also talk about holes, come from. I haven't talked about holes, but we will today. And then P of x is our x-intercepts, because if P of x is equal to 0, then y is equal to 0. So wherever the x value of P of x causes that numerator to be 0, then we have an x-intercept. So when the top of the numerator is 0, then the whole function is 0. But when the denominator function q of x is 0, we have a point of discontinuity. So the first thing that we're going to look at is we could go back from an easy one, the last INB talking about horizontal asymptotes, which just talks about the degree. So I have two polynomials, so I'm going to have two different degrees or same degrees polynomial. So I have this top polynomial and its degree is 0, and then I have this bottom polynomial and its degree is 1. So the degree of the numerator is less than the degree of the denominator, and it has a horizontal asymptote of pi 0. So I could just go down here and put that in. I like on these, like when I find a piece of information, just go plug that information in. So I have a y equals 0. Okay, the next thing is talking about the domain, which leads us to points of discontinuity. If I notice in the denominator, I have x minus 2. So I know my domain, my x, cannot equal 2. So written formally in interval notation, this would be my domain. And it would be a vertical asymptote. So I have a vertical asymptote at x equals 2. And then what I want to do is I want to graph that. And notice the vertical asymptote. I know at x equal 2, the graph is either going to be like up here or down here. It approaches it on one side. And so we can test without a calculator to find out where that's going to happen at. Like, where's my asymptote going to go for this x equal 2 line on the left side and on the right? And this is what we do. It's pretty easy. You're going to just draw a horizontal x-axis. You're going to put the vertical asymptote equation right there. So it happens to go through x equals 2. My function was f of x is equal to 1 over minus 2. And what I want to do is plug in numbers really close on the right side of 2 and on the left side of 2 and plug it into the equation. So really close, I mean really close. So a little bit to the right would be 2.001, and to the left would be negative 1.999. So I'm going to plug those in. And if x is 2.001 and I subtract 2, I get 1 over 0.001, which is about 1,000. Well, not about, it is 1,000. And on the left side, if I do the same thing, I have positive 1.999, and then I subtract 2, get 1 over negative 0.001, which is negative 1,000. So what do these numbers mean? It means when I plug in 2.001, so I'm really close to that vertical asymptote, my graph is up really high. And the opposite on the left side, I get negative 1,000. So when on the left side, really close to the vertical asymptote, my function is going down. We'll make more sense of that if that's not clear right now when we graph that here in a second. it will make sense. So let's go ahead and do that right now. So we said on the right side where it's just 2.001, where is it? It's at 1,000, which is way off my graph, but I know it's going up. And on the left side of this, I was at 1.999 and the output was negative 1,000. So I know it was going something like this. So I know this is the behavior around my asymptote. Okay, the next thing I can do is get my x-intercepts. That's where my numerator is equal to 0. Well, guess what? I have no x values in my numerator, so there are no x-intercepts. There's no value that I can plug into the numerator that will cause it to be 0. Now my next is my y-intercept. My y-intercept is where my x is equal to, and so that's what happens, negative 1. Go ahead and put that on there. And now I'm ready to graph. I know because I have no x-intercepts, this isn't going to cross the x-axis. So it's going to go something like this. Approach it with that end behavior. And I'm going to come right through like this and all the way down. And there's the graph of my rational function. Not too bad. Okay. Now my next one is the second type of pointed discontinuity. We're going to go over as holes for the first time. And so whenever you're trying to find pointed discontinuity, you really want to factor these. We didn't have to factor the last one. So my numerator is x minus 1. My denominator is x minus 1 times x plus 1. Okay? And I notice two things. My domain first, x can equal 1 and negative 1. So this is going to look like an interval notation, excluding those values. Okay, and now the first time you're going to see a vertical asymptote and a hole. They don't have to happen at the same time. You could just have a hole, or obviously you could just have a vertical asymptote. It's just how the factors appear in the rational function. Notice that this function reduces. The x minus 1 in the denominator reduces with my factor in the numerator. So I have this 1 over x 1 when I'm done. When you have a pointed discontinuity reduce out of the function with the numerator, that is what we call a hole. So I know at the or the the pointed discontinuity at 1, because this was the 1 and this is x can equal negative 1. I have a hole there. So 1 comma something, and we'll come back and fill in that something here in a minute. Because when we talk about, okay, well, I know if I plug 1 into this function, I'm going to get a 0 in the denominator, right? So how do we find out what the y value of the hole is? So you're going to plug it into the reduced form. Now remember that find y. Remember, it reduced with the factor in the numerator, which caused it to be a hole. So when it reduces out, now no longer does it show up as a pointed discontinuity. So when I plug my 1 in, right, to this function, plug my pointed discontinuity in there, I get my output as a path. That's where this hole occurs. Now I'm not done, because I still have to talk about my vertical asymptote. So if that was the only point of discontinuity, then all I would have a hole. However, I did have this point of discontinuity at x equals negative 1 from this factor of x plus 1, and it did not reduce with a factor in the numerator, so it is going to stay as a vertical asymptote. So let's go put all this stuff in. So the first thing I know is I have a vertical asymptote at x equals negative 1. And I have a hole in the graph, and a hole in the graph is exactly what it sounds like, 1 comma 1/2. You're just going to put this empty spot. It's just a break in the graph, your graph will still like go through it like it's smooth and continuous, but it's just like a chunk is taken out. That point or solution is just missing. Okay, and so we're going to use the line test to determine the behavior of the graph close to the vertical asymptote. We don't have to do it to the hole. We're going to know how it's going to behave to its hole. Okay, and that was -1. So a little bit after it would be -9.999, and a little bit to the left would be -0.001. I'm going to go ahead and plug that into the reduced form, a little bit friendlier. So I have a -1.001 on the left side, +1. So I have that 1 over -0.001, which is, so I know it's going down. And then on the right side, I have 1 and then -0.999, right? And then what, +1? So I get this 0.001 on the positive side. Positive. And so it's going to go up on the right side. And it always doesn't go up, down on the left side, up on the right side. But it does so far. Going to make it at least agree with my hole over there, right? I guess it could be coming from the denominator. I didn't have any x-intercepts, right? Because my one x-intercept of x equals 1, right? That ended up being a hole. So I don't have an x-intercept there. That's where my, but I do have my degree, right? The degree of my numerator is less than the degree of the denominator, so I know it's here. So I'll add that. And then let's graph this. I guess it looks like we'll definitely have a y-intercept too. I did not do that. So let's do our y-intercept. So our y-intercept, we're going to go to the reduced form again. And we'll plug in 0. So it looks like 1 over 1. And so here I'm going to come down over. There's my hole. And there it is. And then on the right side, I know it just come up around like that. Okay, and that's how I graph my features of my rational function. Just remember, a hole in the graph is caused by a point of discontinuity factor of the denominator reducing with the numerator. They don't reduce out, they're always vertical asymptotes. Okay, thanks.